let's also talk a little bit about the matching story. So these are the perturbative corrections at the scale MQ, so alpha S at MQ. We had perturbative corrections at the W scale when we integrate out the W boson. Now we have another set of perturbative corrections at the heavy quark mass scale when we ever integrate out the heavy quark mass. It's different because we're now passing from something that looked like a full QCD theory with some external operators. We're now passing to this HQET theory for the heavy quark. So if you like, we previously had MW. We knew how to do renormalization group evolution there. And we had a sort of HW theory here. Now we integrate out the heavy quark mass and we pass to an HQET theory below that scale. So if you go back to the kind of HW theory, let me call it that, and we want to match that onto HQET, then we would do it with a calculation like this. And I'll just use this heavy light example still. So here's a matrix element that you could consider for the matching. And let me write it with a bunch of schematic objects and then explain what they are. So the U's are spinners. I'm taking zero momentum here just for simplicity. These R's are residue factors that come in. So far when we calculated the wave function normalization graphs, we just took the divergent piece. And if you do that, when you do the matching computation, you have to use LSZ. And so the finite pieces come back in, and you call them residues. So these are finite residues. That you have to take account of finite in a UV sense. So UV finite residues you have to take into account if you're just using MS bar. And this here would be the vertex renormalization graph. Okay, both diagrams look like this. In QCD, they're both same type of structure. And then in HQET, it's a similar thing. We can write down a formula for the S matrix element for the same states. Now with our effective theory current, and we know how to transition from effective theory and full theory states. Talked about that last time. And so there again would be some residue factors. And if the residue factors are not the same in the two theories, you have to account for that, and they won't be because one of the heavy quark residue will be different than the heavy quark residue here. So this guy here is this finite piece of this graph. This guy here will be the same as above. And this guy here is the heavy quark vertex graph, which is independent of the spin structure. It's not independent of the spin structure up there. So we could carry out the calculations of those loop diagrams, and then we could subtract, and we could see what's left over, and whatever is left over is the Wilson coefficient. Okay, so very similar to what we did before. Calculate, subtract, what you find when you do that is that there's actually two currents. If you consider a vector current, where gamma is gamma mu, then the effective field theory, which is HQET, has two effective theory currents that are vector. So you have C1 and C2. The reason that there's two is because we have another vector to play with, which is V mu. So I can have Q bar V mu replacing the gamma mu. So V mu wasn't an external thing in QCD. It was part of the dynamics. Here it's an external thing, so it's allowed to replace gamma mu as one of the structures. And if you go through the calculation, this is the just to show you what the result looks like. Remember, the heavy to light case is the case where you're not getting a non-trivial function on the right-hand side. So you get a non-zero result at order alpha s for both of those coefficients. Okay. So the reading also goes through this whole thing for the heavy to heavy case, which is more interesting, but it's not really more non-trivial than what we've talked about so far already with the anomalous dimension. You get results that are functions of W. The Wilson coefficient would have functions of W showing up here. Okay? So I won't go through that. Now, if you wanted to carry out this calculation, it looks like it's kind of involved. This graph, this graph, this graph, all these diagrams to consider. You'd like to make your life as easy as possible, and there's actually a very nice trick here for doing that I have to mention to you, because it's kind of magical. So what is the fastest way that I could get this result? So this is a nice trick to remember if you ever have to do a calculation like that, because it's not specific to HQET. So let's pick our infrared regulator to make the effective theory as simple as possible. We have some choice in how to pick the infrared regulator. The result for Wilson coefficients and anomalous dimensions will not depend on that choice. So let's use that freedom and make things as simple as we can. And the choice that does that here is to use dimensional regularization for the UV, as we've been discussing, but also for the infrared. So let's use dimensional regularization for both. If you do that, you can convince yourself that all heavy quark effective theory graphs with on-shell external momentum. So I can take the external momentum on shell. I don't need it to regulate divergences because I'm going to use dim reg to do that. So all the integrals are scaleless. And that means that they come out to be something that, if you think about it, is either 0 or 0 in a way where you have an ultraviolet divergence canceling an infrared divergence, which is still 0. Now, you have to think about the fact that there's both of these going on because you still have to think about adding counterterms to HQET to cancel the UV divergences. But the answers are very simple because you can throw away all the finite pieces. If you have 1 over epsilon minus 1 over epsilon, if you multiply that by epsilon, that term's not there. So 1 over epsilon gets removed by counterterms, and there's no finite pieces left over. So just use MS bar, so you just strip off that exactly. And you're left with 1 over epsilon IR. Now, if you, so the effective theory diagrams are just simply all 1 over epsilon IR. Now, the reason that this is making things simple is because you also know a fact, which is that the IR divergences in the full theory and the effective theory have to match up. So these 1 over epsilon IRs have to match up with your full theory calculation. So if you renormalize the QCD calculation, which you can't really get around doing, you have to do that calculation. So you do that calculation in pure dim reg. Same IR regulator, which is a nice regulator to use for QCD. You do the UV renormalization using the standard counter terms. And what will you get? You will get something that looks like a number over epsilon IR. And then you'll get numbers times logs mu over MQ plus other things. This thing here is just cancels with the, if I subtract HQET, this is just canceling this. So this guy here cancels when we subtract HQET. And so the matching is then just this. So I don't actually even have to consider calculating the heavy. If I use all these facts that I know, if I trust them, then I don't even have to calculate the HQET graphs. I just say, let me imagine that I calculate them. They're all scaleless. They look like that. Let me imagine that I renormalize them. All the 1 over epsilon UVs are gone. I'm left with 1 over epsilon IRs. I do this calculation. I say, let me imagine that these cancel each other. And then I have the matching. So that's exploiting all the facts that we know about effective theories and full theories to get the matching as quickly as possible by just doing the full theory calculation with a particular regulator. It's not checking anything. It's not checking that the full theory and the effective theory have the IR divergences matching up, et cetera, et cetera. But if you know that that's true, if you trust that it's true, then this is the fastest way to get the matching. Seems like magic, right? Okay, so sometimes you can exploit what you know about the effective theory to get things more quickly. So questions about that?
How do you use dim reg for IR?
Yeah, so if you think about the loop integral, then the d here, right, being 4 minus 2 epsilon, having epsilon greater than 0, decreasing the powers of q in the numerator is making it more UV convergent. So to regulate the IR, you want to have epsilon on the other side. So this is what you need for the regulating IR, and this is what you need for regulating UV. So it may seem contradictory that you could even do both of these things at the same time, because greater than 0 and less than 0. But you could always think of splitting up this integral with a hard cutoff somewhere in between, and then just using this above and this below that cutoff. And the cutoff dependence will cancel when you put the pieces back together. So it's actually valid to just do calculations. And for the most part, you can just close your eyes. And you'll get some gamma of epsilons and some gamma of minus epsilons, and those will be separately regulating the divergences. And if you ever worry about it, you can do what I said. You can put a cutoff in and check that you're not making mistakes. But for the most part, it just works automatically. Any other?
Normally, you will get 1 over epsilon UV and 1 over epsilon IR.
Yeah.
You need 1 epsilon UV to be greater than 0 and
Yeah.
epsilon IR negative.
Yeah.
But formally, you can set epsilon UV equal to epsilon IR.
That's right. Yeah. So formally, this is 0. And the reason that you have to worry about 0 is because you have to add a counter term to cancel this. Your UV counter term, you have to still add it. And then it cancels this, and then you get something non-zero. So the bare graph is 0. The counter term is non-zero, and the renormalized graph is non-zero. So it's a subtlety that's worth remembering if you ever want to do calculations this way.